Hi, this lecture is an introduction into rotational dynamics. This is applying forces to things, to objects to make them rotate, and that rotation leads to angular momentum and rotational kinetic energy. Before we do that, we're going to need to talk about moment of inertia, because when we talk about objects rotating and using torque, we're not going to be using the mass of the object anymore, but the object's moment of inertia. This is a rotational equivalent to mass. Okay, then we'll look at rotational forces and constant acceleration, and then momentum and energy in separate PowerPoint slides. Okay, so when objects rotate, okay, that motion needs to be accounted for differently from linear motion, because if I think about the little points of mass farther out, okay, those pieces of mass will have different speeds compared to points closer to the point of rotation. And so because of that, they'll have different momenta and they'll have different energies in terms of like 1/2 mv squared or mv. Okay, and so that needs to be accounted for. And the way we account for that is by calculating the moment of inertia of the object. Okay, and that moment of inertia will be used instead of the object's mass m, okay, but we can then multiply that by angular velocity or angular acceleration to get our energies and our momentums. Okay, so how do I calculate the moment of inertia? Okay, moment of inertia just like is the complete similarity to mass. Okay, it's the resistance to rotational acceleration. Okay, for just a single point mass, okay, the moment of inertia is going to be that mass times r squared, where r is the distance from the point of rotation, whatever that distance happens to be. When I have multiple point masses, okay, then the moment of inertia is the sum of all those individual points, okay, mr squared here plus mr squared there. Again, the distance to the rotation, okay. When I have solid objects, okay, that sigma sign now becomes an integral sign, okay? So now it becomes integral of mr squared dr, okay? If the mass changes with radius, okay, you need to be careful with that, okay? Then we need to account for that as mdr, and we'll talk about that in upcoming PowerPoint. Okay. So here's an example, okay? I have a rod of mass m and length l, and I rotate it about its center, okay? In that case, what I'm going to be integrating from is from minus L over 2 to L over 2, okay? The m over L is the density of an individual point mass, because I'm going to look at little slivers of mass. Assuming the rod is thin enough, okay, then my point of rotation is the axle right in the middle. Okay, and I have a little sliver of mass at, like, 1/10 of a 1 millimeter away, then 2 millimeters, and then 3 millimeters. But all those points of mass have the same mass. Okay, and that mass, when I look over the whole bar, is m over L times that little dr. Okay, so that's where this equation comes in. After I go through the calculus, I find that the moment of inertia for a rod rotated about its center is 1/12 ml squared. Okay, this is different from the moment of inertia for the same rod rotated about one end. And we see that very easily in that if we ever try and rotate a hammer or something like that, it's a lot easier to rotate it about its center than it is to center of mass than it is to rotate it about one end. So if I calculate this for a rod of mass m and length L again, rotated about an end, the integral is shown there. It's very similar. It's just I'm integrating over different values. Instead of minus L over 2 to L over 2, it's now 0 to L, because 0 is my rotation point. Okay, so solving this, I find that now my center of mass of rotation is 1/3 ml squared. So when an object rotates about its center of mass, that's always going to be the smallest moment of inertia possible for that object. Okay, everything else is going to be larger. And that brings us to the parallel axis theorem, because this is another way I could have calculated the moment of inertia rotated about the end. Okay, and the parallel axis theorem basically says this, that the moment of inertia of an object rotated about any other axis parallel to its center of mass axis can be calculated using this formula, where the new moment of inertia is equal to the center of mass, that minimum, plus this mr prime squared, where r prime is now the distance between the two axes. Okay, so looking at that rod example, okay, the rod through its center of mass was calculated to be 1/12 ml squared. But the rod through its end now is 1/12 ml squared. The r prime now is L over 2, remember, because I'm now rotating it about one of the ends. Okay, and so it becomes 1/12 ml squared plus m L over 2 quantity squared, or the same 1/3 ml squared. Conceptually, it's important to remember that it's always going to increase as I move farther and farther away from the actual center of mass. The moment of inertia will constantly increase as I move farther away. So here's another example, which is a circular example. Okay, so I have a disk of mass m and radius r rotated around its center. Okay, in this case, what I'm going to be looking at are disks. Okay, little, very small, very thin rings as I move farther and farther away. Why do I use rings? I use rings because everything in that ring is going to have the same R. Okay, so the density of that, the mass of that ring, as I move farther and farther out, my delta R's of that ring, or how thin that ring is, stays the same, because that's the way calculus works. Okay, but the circumference of that ring increases, so my mass increases for those rings as I move farther and farther out. So mass is going to be a function of R, and I account for that by taking the density, which is the mass divided by the area, times the circumference, 2 pi r. Okay, r squared is the part in the mr squared. Okay, dr. And when I integrate all of that, I find that my moment of inertia for a disk rotated about its center is going to equal 1/2 mr squared. Okay, it's worthwhile to try your hand at a few of these things just to get used to it. Most of the time, the AP Physics C will give you the moment of inertias, so you don't have to spend the time calculating it. But it is important to remember, okay, the parallel axis theorem, because they could very well ask you, and you need to understand, as long as I move away from that center of mass axis, my moment of inertia will increase. Okay. So when I use torque, okay, to make an object rotated, a force that is perpendicular to the axis of rotation and to the r vector, okay, r being where I apply it to that point of rotation, okay, and so when I apply a force, a distance from the axis of rotation, okay, that's going to be torque. Officially, torque is going to be the r vector crossed with the f vector. Okay, and the cross product differs from the dot product. Okay, we talked about the dot product earlier, but the cross product, the result of a cross product is another vector, whereas the result of a dot product was a scalar. Okay, so this is the way I suggest you solve for the cross product. Okay, in that the magnitude of the cross product is going to be a b sine theta, magnitude of a times the magnitude of b times the sine of theta. Okay, the direction of the resultant vector is going to be perpendicular to both a and b. And to figure out which direction, because there are two directions that will be perpendicular to both, okay, think of it as into the page and out of the page. That's where the right-hand rule comes in. We've come across the right-hand rule. Hopefully you still remember it. We went across it in electromagnetism, okay? But just to go over it again, you put your open hand flat along A and rotate it towards B in this case. Okay, but it's easier to simply remember whether a torque is clockwise torque or counterclockwise torques. Counterclockwise torques are generally considered to be positive. Clockwise torques are generally considered to be negative. After that, all your torques can simply be positive if you remember to change the sign for clockwise and counterclockwise. Okay. The second method to do it is this long drawn out method. Okay. I don't believe that the AP exam will require you to do it. I just show it here to be complete. Okay. Thank you very much.